Hello everyone. In this video, I'm going to be talking about Proton NMR and the associated type of problems that you'll be responsible for being able to answer on the exam. I'll go through some example problems at the end, but I'm going to go over in general over kind of what you need to understand, what you need to identify with, what you need to memorize, and kind of not really the concept. I'm not really that strong on the concept, just like with IR, but I'm going to go over try to explain it in a way that makes sense of it. So, Proton NMR is proton nuclear magnetic resonance, HNMR, and purpose, as it says over here, it basically allows you to, given on what's on the graph, lets you figure out everything that is present, and it gives you all the information that you really need to figure out how the things are connected together. And the way it works is it works through basically the chemistry of the hydrogen bonds connected to every single carbon. So if a carbon has hydrogens on it, we use that information and it'll give us information about the carbon, and it'll also give us information about neighboring carbons. So we'll get information about whether or not the carbon itself has protons on it, and then we'll get information about whether the neighboring carbons around that carbon has protons on them. Okay, so it's using the protons to figure out everything. Okay, and the way this graph works is every region on the graph is specific to certain ranges of molecules. Okay, and I don't really. I mean, this is not a bad graph, but it's good to make your own and kind of. And this one has way more than what you're responsible for. Okay, so this has a lot more than what you need to know, and this is kind of like at the end of Orgo 2, where it has all this stuff. And really, what you're going to be responsible for is double bonds, benzene rings, not really halogens, carbonyls. I think, not really sure about esters. I don't think esters. But yeah, you're going to be responsible for very minimal, okay? And it's going to be pretty simple. So I'll go over that and I'll explain it a bit. And let's just first plop out let's first talk about kind of how this works, okay? And this might be best to do with the, I guess I'll just talk about this then. Okay, so I'll talk about the ranges later on when we're looking at this table more. But there's two components of this table, okay? There's going to be an integration number, which is a number that's going to be over every single peak. And then there's going to be another thing that you count. It's the number of splits. So there's integration number and there's number of splits. The integration number is, I mean, you have everything for you if you have this worksheet and you have it. It tells you how many hydrogens are on that carbon that you're looking at, okay? So if I have a CH3, the integration number should be 3, okay? It should not be, yes, it should be 3, okay? And then the number of splits is going to be the number of hydrogens that are surrounding that carbon plus 1. So what you're going to do, you're going to count the number of peaks, and then you're going to subtract 1. And I know this kind of doesn't make sense when I'm not giving any substance, but we can look at some examples very quickly. Go down over here. Okay, so this is how it typically will look like. So this is a harder example, but this is how by the way, the big problem at the end, it'll give you an IR and it'll give you an NMR and it'll give you a number, and you're going to be responsible to figuring out how the molecule looks like, and you put that molecule over here. Okay, so what this looks like, you have this range, okay, and you're going to be familiar where things are plopping down on this range. And the number on the top is giving you the number of hydrogens that are on the carbon that is being looked at, okay? The number of peaks refers to what's surrounding it, so it's environment, okay? So if I have 3 peaks, which it's a shitty graph right here, honestly. This kind of looks like 1 over here, 2 over here, and 3 over here. So 3 peaks, and then I subtract 1, and so that gives me the number 2, and so that means there's 2 hydrogens adjacent, okay? So there's 2 hydrogens on the carbon nearby. So that's the information that's given, okay? And then you might ask, well, how do I know it's not 1 hydrogen on one side and 1 hydrogen on the other side? Well, the way that we know this is because the way Proton NMR works over here is when you have combined environments, and this won't happen for this really too much. It will happen. You have like complicated things like what we're having over here. Um, but usually it's what's next to it. Let me see a better way to kind of, I guess, introduce this. Um, might be better if I look at, where is it? This is very good. Okay, so this is strictly NMR, Proton NMR. And so what we're doing over here, we're looking at every single environment, all right? And the peaks are representative of the multiplicity values of those carbons. Okay, so where she's doing over here, she's saying you have carbon A, B, C, D, whatever, and we're looking at HA. Okay, and I'm going to go to the drawing pad really quick. All right, so if I have CH2 like this, and I have another CH2 like this, and then I have CH3, all right, and I have these. So I have a CH3, have this CH3, and let's say she wants to know the multiplicity value for the hydrogens on over here, and she calls this, whatever, HA, right? How do I know she's not referring to this top carbon or versus this one, bottom one? Well, they're actually the same, right? So whether this hydrogen, even though this has two hydrogens on it, she's just going to refer to them both as HA, depending on what letter is there that she gives, B, whatever, C. They're both the same because they have both the same chemistry, okay? So this environment right here and its hydrogens, these two are the same, right? They're both the same chemistry-wise. So whether I'm talking about this one or this one, they're both referred to as HA, okay? And the same thing goes for these over here as well. So this one is also, this is a symmetric molecule. These would also be HA hydrogens, okay? And there's special rules for all this that I'll have to go into. But let's say this side was not symmetric, okay? Let's say like it kept going on and I had more molecule and I just had this side. And the way I calculate the multiplicity value is going to represent the environment surrounding this carbon, okay? And like I said very quickly for how it looks in the final part, right, how it looks for the big questions at the end, you're going to actually get these peaks, okay? And this is going to be the integration numbers, number of hydrogens on the carbon that you're looking at, and the number of peaks is the environment, and you subtract one, that gives you the number of hydrogens that are nearby, okay? So the formula, right, let's go up, okay? Formula is number of splits equals number of equivalent hydrogens, carbons plus 1, okay? And so when I get to something like this, right, and let me go back to my drawing. If I'm trying to calculate the multiplicity, aka the number of peaks for the environment around here, right, what you do is I go to this carbon. This carbon is unique and has hydrogens that are unique on it. And I look at this carbon over here, it has hydrogens that are unique on it. So I have two unique hydrogen environments over here and over here, and I need to calculate the multiplicity for each, right? And so, not the multiplicity, but the value, okay, the split value. And so what you do is you count the number of hydrogens that are present, okay? So 1, 2, 3, and I have 3, and we add plus 1, okay? And I'll put that in parentheses. So this is referring to, should use different colors, honestly. This is referring to this right here, all right? And so this is going to represent this carbon to the left, right? And then over here, I have to look at a different one. I have to look at this carbon right here. And let's say it was a unique carbon. It was not the same as this carbon right here, chemistry-wise. It has other things on it. It's very different from this left side of the molecule. It has 1, 2, okay? And so I'm going to have 2 plus 1, okay? And this is going to correspond to this guy. Okay, and now I'm going to multiply them together. All right, because now I have two different environments and I multiply these values together, so I get 4 times 3, and my total number of peaks is 12. All right, and this is how it's going to work over here. The representation is a little bit different on the graph questions. I think they simply add them all together, so you would have 3 plus 2 and you would get 5 peaks. But still, it's going to look like a lot of peaks, and you'll know that there's a lot of the environments nearby. And I explain this a lot better in person because it's kind of just you have to look at it and we look at it. It'll be better towards the end of the video, I promise, where I do some examples. But this is how the first part is going to work. You're going to have this multiplication together, and you're going to look at each unique environment that's surrounding this carbon here with its hydrogens. Okay, and this is going to give us information about the nearby environments. So let's look back at our problem over here. And this is what we're going to be doing. So just to do this by example, I'm going to just copy and paste this. All right. All right. So let's just do this together. So number of distinct protons. So number of distinct protons, so unique, chemically unique protons that are on this molecule, right? And this will be a good showcase of how to identify things that are unique, and this will also help you figure out if I have to like multiply things together or if I just summing things up, right? Because if things are the same, then you're just adding them up and then you're adding 1. But if they're different environments, then you have to multiply each one of those plus 1 thingies together, just like I did a couple seconds ago. So let's count the number of distinct protons. And basically, if it's not symmetric, then it's not then it's distinct. Okay. So if it's not symmetric, then it's distinct. So I have a group coming off of this benzene ring right here, and I have another group coming off of here. Now there is no way for these hydrogens to be for this to be symmetrical at all now. Okay, so the hydrogens are all unique. This hydrogen's on a carbon that's next to this. This hydrogen's on a carbon that's next to this. This hydrogen is on a carbon that is next to this and close to this. So everything has its own distinct chemistry. So this is going to be 1, 2, 3, 4. This carbon has no hydrogens. Okay, this carbon does have hydrogens. CH3, 5. Okay, so each one of these hydrogens these are all the same. Even though there's 3 over here, they're all the same. So this is just 5. Okay, and now I have these hydrogens that are over here, 6, 7. They have their own stereochemistry. One is, relative to the other, they're very different. Okay, so each one of these is chemically unique, even though it's on the same carbon. We're not used to that, but they are unique. So this is 5, 6, 7. Over here, I have a CH2. That's unique. That's 8. And now I need to be careful because now she's going to do this. She's going to draw things weirdly to make things seem different, but they're not. Okay, so then I have the CH, and that's 9. Okay, and then I have a CH2, CH3 group coming over here, and then I also have another CH2, CH3 group over here. So really what I have is an not an isopropyl, but I have maybe I think isobutyl. Okay, so I have these symmetric CH2, CH3 groups that are both the same. So I only count each one of those hydrogens once. This is 9, 10, and 11. The answer should be 11. If I'm wrong, then I need to go review. But I think I'm right. Right? So I have these unique hydrogens, and these are all the unique ones. I've numbered them. And now she's going to ask you specifically the ones that she chooses. She's going to ask us the multiplicity of them all. Okay? So multiplicity of HA, and HA is right here. Okay? And so I need to look at this carbon, and the multiplicity is referring to the carbons that are adjacent. So I'm looking at the carbons that are directly bonded to this carbon. So carbon A, even though it's HA, it's referring to the carbon that these hydrogens are attached to. They're attached to this carbon, so I'm looking at over here, and I'm looking at over here. So I have 2 things that are bonded to this carbon. This carbon does not have any hydrogen, so I don't care. Okay, right? And if I were to calculate the multiplicity of this, it would be 0 plus 1, and this would just be 1, And so it doesn't really matter because 1 times 1, you know already. It's not going to contribute or affect the value that comes out of this, okay? But it would be represented by a single peak, right? Nothing over here, but I do have something over here. I have 1 hydrogen over here. So this is going to be 1 plus 1 equals 2. And 2 sometimes can be referred to in keys as D for doublet. So this can be D or 2, okay, doublet, okay? And now multiplicity of HB, HB is right here, and I need to look at everything around it. Okay, and this is a great example. So I have a carbon right here. Let me just draw something out. Okay, so I have this group, I have this group, right? And then I have bonded to it, I have another thing, and I have some other R group. Okay, so on each one of these things, I have a hydrogen. I'm just redrawing what we have. Okay. Okay, so and the bottom one's exactly the same, and then over here I have 2, right? And this one has 1 hydrogen itself, and they're asking for what's the multiplicity of this hydrogen right here. So we're looking at the environment that's surrounding this, and we're asking, okay, so we're trying to characterize the environment that's around it and the number of hydrogens that are there. Okay, so I have these, and what we said before, we said that we add up the hydrogens that are on the adjacent carbon. So this carbon right here, this carbon right here, and this carbon right here. Okay, and I add up the adjacent hydrogens, and then I do the +1 thing, and I multiply them all together and get some big number. Okay, but we have to be careful here, because so let's do this one at a time. So the parentheses for this one is going to be 2 plus 1. Okay. Now, the parentheses for the next one is going to be from right here. Let me use a different color. All right, so I have to calculate. So I have 2 and plus 1, right? But this is actually wrong, okay? And the reason it's wrong is because if I were to calculate the next one over here and do another 2 plus 1, it's actually going to give me the wrong answer. And what I actually have is, because they are symmetric and they are the exact same chemically, these hydrogens are going to sum up. So it's going to be as if I have 4. So instead of 2, I actually have 4. So I have 1, 2, 3, 4, and I add them all together even though they're on different carbons because they are the same chemically. And then I do plus 1. And so I get 3 times 5, and this gives me 15. Okay? And then you would put that. There's no like thing for it. What she would write out in letters either this would be 15, and so this would be triplet, and then this is 5. So, but this doesn't really have a letter for it. Okay, so triplet is for 3, but the answer is 15 for this. Okay, so I hope everyone sees how that works. So it combines both the hydrogens because they are chemically the same, and this one is distinct, so we multiply it. Everything that's distinct, you multiply them together, and everything that is the same, you add them together. Okay, multiplicity of HC. Multiplicity of HC, so it's this carbon right here, and this carbon is next to, right? It's next to this one. But this is symmetric again. So I have HC is, let's see. For this one, you do not add them together, okay? It's different when I'm looking at carbon, this carbon B, and I'm looking at what's around it, right? That's when I add things up. But when I'm specifically looking at the individual group itself, I'm not going to have to multiply them together, okay? That I'm looking at what's around this carbon right here, and what's around it is just this CH2 group, okay? And so this CH2 group is the only thing that's there. So it's just going to be 2 plus 1 for this, and it's going to be 3. or triplet, okay? And then lastly, the multiplicity of HD. And HD is going to be this carbon right here, right? And I'm looking at the carbons that are bonded to it. So I have this carbon is the only thing that's bonded to it. And this carbon has 0 hydrogens on it. And so it's 0 plus 1. And that's just 1. Okay, so this is singlet. All right? I hope that makes sense. I did an exam before this just to make sure I was doing everything right. And I'm pretty sure I did everything right. But we can look at an exam really quick. Okay, so this is a 2015 exam. This was my exam. Didn't like this exam very much, but it went well, and it should go well for you as well. But let's look at what she has over here. Right, let me just copy and paste this. All right, so here's the problem over here. So this is how it will look, and then she'll have, this one's a little bit unique because we have a different thing over here. We have an alcohol on here, and that changes things a little bit. The only thing different with the alcohol, you have to introduce different type of conditions, and we call this ultra pure conditions. And ultra pure condition just means that I can the alcohol hydrogen will only be considered just as an adjacent carbon's hydrogens would be considered, and it is only considered when it's in ultra pure. Okay, so only in ultra pure will I be able to count the hydrogens on alcohols as within my multiplicity values. Okay, and all right. Okay, so now let's look at them. Multiplicity of HA. So HA is right here. Okay, HA is this hydrogen bonded to this carbon, and I have to look at if I have any distinct environments next to it, and I'll multiply them together. So this carbon, and then it's bonded to this carbon. This carbon has 0 hydrogens on it, so I'm not looking at anything over here. But I do have this distinct, sterically, distinct, not sterically, but called whatever, stereochemically distinct hydrogen. Okay, so I'm going to have this one, and this is just going to be 1 plus 1, right? And this is just going to be 2, and so this will be a 2 over here. This will be a 2 or a doublet. And then now we look at the multiplicity of HB. HB is this carbon right here with these hydrogens. And look at the adjacent over here, there's no hydrogens, and over here there's no hydrogens. So this is going to be 0 plus 1. On all sides I have this 0 plus 1 value, and this is going to be 1, which is singlet. Okay, so this is just singlet. It could be consistent, 1 or singlet. Okay, multiplicity of HC. HC is this carbon right here, right, this hydrogen, and I have to look at the environments that's surrounding it. So on this side, I have this carbon has 2 hydrogens, so this is going to be 2 plus 1, okay, times, right? And so these CH3 groups are the same chemically, right? So I have to add up all their hydrogens. So 3 plus 3, that's 6, plus 1. So what I get is 3 times 7, right? So that's 21, right? And let me check. All right, so far so good. So that's 21. And now let's look at this one, multiplicity of HD. Now I said the first 3, everything in part I is done under normal conditions. So I don't consider this hydrogen on this alcohol within my multiplicity values. Okay, I ignore it. And so CH2, I look at this, it only has a CH2, so it's 2 plus 1. Okay, and that's 3 or a triplet. So 3 or triplet. And let's check triplet. All right, multiplicity of HD, but now we're looking at an ultra pure conditions, and now it changes. So now I still have that 2 plus 1 value, but I have it multiplied with the 1 hydrogen on that alcohol. So 1 plus 1 over there. And so now I have that 3 times 2, and that gives me 6. Or it can be written as a triplet, triplet, doublet. Okay, so this is just 3, and this is 2, and this is triplet, doublet. So either 6 or sorry, triplet, doublet. And I think that's how she writes it, triplet, doublet. Okay, so that's how this problem works. Okay, that takes care of everything for this problem. It's just you're looking at the environments. We're using the hydrogens around everything and all the things to figure out everything that we need to know about this molecule. All right, and it pieces together like a puzzle, right? And it'll make a lot of sense once you combine this with IR and we learn some other components of how to figure things out. Okay, so I'm going to jump now to an actual problem, and I'm going to use the workbook for that. All right. All right. So let's take a picture of this. And this is the main problem because it has the most points attached to it. Okay. So, all right. Cool beans. All right. So this is how it's gonna look. All right. We're going to learn as we go. The best way to learn is through problems, right? So I'm going to keep teaching you a little bit more about IR and little tricks and spec through the problem and NMR. And I'm going to just show this, and then before I go on, I'm going to define the different regions and how to look at and understand the graph. Okay, so this is how it's going to look. And one thing I want to start first is she's going to give you this, and she's going to give you the IR, and she's going to give you the NMR. Now, this is an important part. So there's a 3-step process for doing these problems. Okay, first you look at the formula, then we look at the IR, and then we look at the NMR. Okay, the formula itself will give us information, and if you were attending last class, Renee already did it, but we're going to calculate the unsaturation number. And what the unsaturation number is, and what it will give us is, it'll give us either the number, for every unsaturation number, it represents either a ring or a double bond. Okay? And for every 2 unsaturation number, once we have 2 or more, it can represent a variety of things. But a triple bond is represented by 2 unsaturation numbers. Okay, so I'm just going to show what I mean instead of this hopscotch, what I'm just saying. The unsaturation number formula is, it's an ugly line, is we're going to do the number of carbons, okay? And we're going to multiply that by 2, okay? And then we're going to add 2 to that, and then we're going to subtract the number of hydrogens, okay? And then if we have any halogens, we're going to subtract those. So I'm going to put X because halogens are usually represented by an X, okay? And we're going to ignore all oxygens, and we're going to divide by 2, okay? So if I do this for this right here, I'll get 5 times 2, that's 10, plus 2, and then minus 10, and all divided by 2. And if I do that, I get 12 minus 10, so that's 2, and so I get 2 divided by 2, and this is 1. I have 1, the value of 1 means I have either 1 double bond or 1 ring. And likely when you have it this low, and this is in the worksheet, the workbook, it means it's usually always a double bond. Okay, and this can be expressed as any type of double bond, alkene, carbonyl, anything. Okay, so when it's 1, when it's 2, that usually means you have double bonds. Okay, but once it reaches 4, if you have an unsaturation number of 4, it's always, almost always, always. So when it's 4 or more, it's almost always a benzene ring. Okay, and this thing itself is represented by a saturation number of 4, because I have 1 ring, that's 1 saturation number, and I have 3 double bonds, that's 3 more saturation numbers. So this whole thing represents a total of 4 unsaturation numbers. Okay, so that's just something you need to know. So I got some information from the molecular formula. Now I know I have one double bond somewhere in the molecule. Okay, so I'm going to stop there for a second, and I'm going to show some things about the different ranges, about this ppm, parts per million region over here. Okay, where the peaks fall. Okay, so let's just draw ourselves a line. Okay, And I'm just gonna put 1, 2. Not the best drawer here, so it's gonna probably piss you off because the numbers are not spaced evenly if you're OCD. 7, 8. Okay. For now, we don't really have to worry ourselves too much. Okay, all you're gonna be really responsible for is just knowing benzene rings, just regular carbon hydrogen bonds, um, things about de-shielding or downfield, and I'll explain what the heck that means. And then really nothing that much, and just alcohols, how to place alcohols and stuff like that, and what they look like. Okay, so the moment the only thing you're responsible for knowing is in the 7 and 8 region, and this is where we're going to have our little friend Mr. Benzene represented. Okay, and the only type of benzene ring that you will have represented, right, is going to be what we call the para substituted benzene ring. Okay, and it looks like this. I'm drawing out the hydrogens just to show you what it looks like. Okay, so I'm going to have the para substituted benzene ring. This is the only one really that you're going to be expected to understand yet far. Okay, as far as I know, it's never been anything more. Because this is strictly Orgo 2. This is even pushing it as it is. And so the way this is going to look like, it's going to look like this. Okay, so it's going to look like this doublet peaks. Okay, there's going to be 2 of them, and each one of them is going to have an integration of 2 on it. Okay, so 2H, 2H. So each one is just saying there's 2 hydrogens. Okay, and sometimes it can be rewritten as a total of 4H because they're symmetrical. Okay, and to correspond this to then the peaks itself to the molecule, what we have is we essentially have a symmetric molecule straight down the middle. Okay, so straight down the middle, I have a symmetric molecule. So the things on this half are symmetric. The things on the top are the same, right? This hydrogen are both next to this R group. So this and this are the same, and this one are the same. Okay, so what that means is that I have a total of 2 hydrogens here. Okay, so this means 2 hydrogens, and it's only bonded to one hydrogen, right? And so the multiplicity value is only bonded to 1 hydrogen over here. So integration number is 2 because this peak is corresponding to two locations, right? So 2 hydrogens are represented by the peaks, right? By the multiplicity value, and the multiplicity value is only respective to this other hydrogen here. So because it's symmetric, right? It's only 1 plus 1. You don't really understand this, but it's nice to know when it makes sense. So this is 2, and this is why this is a doublet. So I have 2 peaks here, and this is why I have that. Okay, so total of 2 hydrogens because these are both the same, right? So that's why the integration number is 2, and then the multiplicity value corresponding to this one is just 1 plus 1. Okay, and it's reflected on both sides. So both sides have this. So this one is unique, and this one is unique. This is not unique. This is not unique. So I have hydrogen A, hydrogen B. This is for hydrogen. I'm not sure which one is for which, but Renee might know probably. But this is for hydrogen A. This is for hydrogen B. Okay, and so that's just why it looks like that. Anyways, just a little bit of explaining. All right, so this is always going to look in the 7-8 region. You're going to have the doublet peaks. Okay, now that's the only really structurally unique type of thing. All right, there's 2 more little things, but besides that, nothing really. Now, everything in like the 1 to 3 region is going to correspond to just basic carbon hydrogen bonds. So you'll have a lot of different peaks over here. And there's something unique that happens, and we call this downshielding or downfielding, deshielding. When these peaks are stretched to the 4 region, so like the very like 3.5 to the 4-ish region and above, this means that these carbon hydrogen groups are adjacent to something that's very electronegative. So either it's usually an oxygen for your case, so an alcohol in particular, or an OR group, or a halogen. Okay? And so this means that, let's say I have an integration like this, right? And let's say I have like, whatever, let's say I have like a 2H over here, okay? And I have this like 2 peaks, that means next to another hydrogen. So it means I have like a CH2, right? That's next to like a CH, but this means it's also next to something that's very electronegative. So there's also an oxygen bond over here. And so whenever you get these peaks that push down to the 4 region, right? Around 4, that means it's bonded to either an oxygen or an OR group, it's oxygen or a halogen, okay? But most of the time it's going to be these, right? And so that's one thing. That's downfielding, and because things are electronegative, they're going to pull them to the 4 region, and that's what that means. Okay? So if this is kind of like out of place or vague, because I'll need to show you with the problems. And then the last kind of weird thing that you really need to know is when you have a singlet peak that has an integration value of 1H on it, this always means OH. Okay? This always means OH. And so that's what that refers to. And then the last and final thing, between the let's see, it's between like the 5.5 and the 4.5 actually. No, 5.5. The 5.5 and the 6.5 region, you will have in here is where you'll find your double bonds, so alkenes. Okay? And these can be represented weirdly because of the way they work and the multiplicity values, the way they work. And usually it's represented by multiple like peaks. So you'll have like different ones. Okay, and it'll be easier to show through example rather than me trying to show it. But yeah. Okay. So that covers everything. So just need to know the regions where these peaks fall, and this will tell you what kind of groups. So we're in the 6 region-ish, like 5.5 to 6.5, that's double bonds. 7 to 8, this is where the benzene ring is in the para sub. 4 region means always things that are connected to electronegative groups, and everything over here is just CH bonds. Okay, and that's what you really need to know for this exam. So now let's go back to our problem. So I already found the unsaturation number is 1, and now I'm going to go to my IR. And I'm going to see over here, I have, this is the 1500, so this is all fingerprint region. I don't give a crap about it. And over here I have 1500, 1600, 1700. This looks like 1750. Okay? So 1750, I have a very, very sharp, very deep peak. This automatically means I have a carbonyl. Okay? And so now I've already taken care of, do I have a double bond? Do I have a, a alkene? I have a carbonyl, okay? So now I know I have a carbonyl in my structure, right? And now finally, I've gotten all the information I can from the IR. I don't give a crap about anything else. Nothing else is really going to be significant. And now I'm going to look at the NMR. So now I'm going to show you the way we look at this. It's a puzzle. So I don't have anything electronegative, okay? So this is 2.5. Nothing is in the 3.7, 4, 4.2, 4.3. I don't have anything like that. But I do have these weird numbers, okay? I have 4H and I have 6H. Whoa. That kind of strikes me as weird. I can't have, this integration number is supposed to represent the number of hydrogens on a carbon. Obviously, I can't have four hydrogens because that means it's just a CH4, and obviously I have a molecule, and I can't just have a CH4. So that's weird. And then I have 6H, and obviously I can't have something that has 6 hydrogens on it. So like I showed before in the previous problem that was just strictly NMR, the integration number is going to refer to all the hydrogens that correspond to the multiplicity value, right? So for the benzene ring, it's 2H because there's two hydrogens that correspond to the multiplicity value. And so what this means is I have symmetry, right? It's always means symmetry or similar environments. So 4H means that I have, you know, some carbon, right? Some carbons, and they're both CH2s. So what this means is I have a CH2 and I have some carbon over here and I have another CH2. And both these CH2s are bonded to the same exact environments, okay? And so that means what it's bonded to over here is, let's first see what the peaks represent. So this is the number of carbons that correspond to the carbons that we're looking at. And then the peaks are going to tell us how many hydrogens are around it. So I have 1, 2, 3, 4. And so this is saying that these environments are symmetric and each one is surrounded by 3 hydrogens. Okay? So maybe I definitely know now that they can't be both bonded to the same thing. This can't be a CH3. That wouldn't make any sense. So I know that's not right. Okay? But I do know I can have another attachment on this side. So I can have this CH3 on this side. And that means there's another one on over here. Okay? And I'll show you my logic. And this will all piece together once we look at this peak as well. Okay? So the integration number can be more than 3. And that means we have symmetry. Okay? So you have a CH2. They have the same symmetry. So together it's 4 hydrogens that correspond to this peak. Okay, and both of them are next to a CH3. All right, and then if I look over here, I have 6 hydrogens that correspond to this peak. So a total of 6 hydrogens, 3, that's 6, and they correspond to 1, 2, 3 minus 1, that's 2. So both of them have a CH2 next to them. So CH2, CH2. And so now we have that symmetry, and it makes a lot of sense now. And now we're missing something, right? So I have 5 carbons. I have 1, 2, 3, 4, and obviously we have this connecting guy over here, right? I know I have this connecting guy over here because if I had something else that had hydrogens, then I would have a lot more peaks because then I would have a unique environment over here that has hydrogen on it. So don't forget my carbonyl. So now I'm at the end of the line now, and I need to figure out where my carbonyl is. And I know that I have this connecting carbon because otherwise it wouldn't make any sense. And so I know my carbonyl is over here, and I know my structure looks like this. So 1, 2, carbonyl, 1, 2. And that's my answer. So I've now obtained the molecule and what it looks like. And so this is how it works. Other ones are more complicated than this one. This one's a symmetric one. Only tricky thing is if you're not familiar with this symmetry. And I'm glad this is the first problem because this is one of the trickier things that comes down the line. But we will be doing more problems tomorrow. This is just an overview. And I might do more problems later, but the video is already kind of getting long. But if you have questions, of course, just try to reach out to me, and I will do my best to answer them. And I will let you guys know when I have office hours and stuff. Best of luck, okay?